Good morning, everyone. So we will start with the problems of chapter 10 about the rotation of a rigid body about a fixed axis. In this chapter, we're going to solve a list of problems that I put in one file, and you have them on Teams. So we have plenty of problems. اللي رح نعمله إنه رح نبدأ بالproblems من الأسهل للأصعب. وكمان حسب الترتيب يعني اللي أخذناهم بالكورس من definitional angular variables مرورا بالconstant acceleration لعند الرولينج موشن يعني للأخير. ورح نمشي فيهم من الأسهل للأصعب، بمعنى أنه من الإيزي نقول عند المور شوي sophisticated problems. وفي بعض البروبلمز اللي حيبينوا معنا مش بالضرورة نحلهم مباشرة أو بالأول، بس إذا بقي معنا وقت رح نحلهم بعدين. أوكي، سو مش بالضرورة نمشي بنفس الأوردر الموجود هون حسب الفايل يعني. So let's start with the problem 13. We have a wheel 2 meters in diameter, lies in a vertical plane and rotates with a constant angular acceleration of 4 radian per second squared. The wheel starts at rest at the time t equals 0, and the radius vector of a certain point P on the circumference of the circle of the wheel makes an angle of 57.3 with the horizontal at this time, which means at the time t equals 0. Now, at the time 2 seconds, you have to find the angular speed of the wheel, which is omega, the tangential speed v, and the total acceleration of the point P. And finally, you have to find the angular position of the point P. So let's move to the whiteboard. In this problem, I've written the basic given. So we have a wheel of diameter d equals 2 meters. هون دغري حطيت مباشرة استنتجنا الراديوس. You can do this. هيك بترتاحوا فرد مرة بتلاقوا شو الراديوس بتصيروا تستعملوه. قالوا لنا إنه the wheel it rotates with a constant angular acceleration of 4 radian per second squared. So we have alpha is equal to 4 radian per second squared, which is constant. Now at the time t equals 0, قالوا لنا إنه the wheel starts at rest, which means that omega 0 was equal to 0, and it was making an angle 57.3 with the horizontal line. You have to find at the time t equals 2 seconds omega in the first part. You have to find the tangential speed اللي هي v, and the total acceleration a, and finally you have to find the position of the point at this time. So let's start with the first question, part A. Before to do so, in any problem, since now we have seen a lot of types of motion, يعني من translation, uniformly accelerated rectilinear motion, for example, شفنا كمان الروتيشن، شفنا الرولينج. So you have first to define the type of motion. هلا هون نحن هو already بالgiven قالنا انه it rotates with a constant angular acceleration، يعني اعطاك هون it defines the type of motion. It's a rotation under a constant angular acceleration, and you know in principle how to solve such problems because you know everything about it. You know the kinematic equations that can be used for the case of a motion under constant acceleration. And so if we need to determine omega at the time t equals 2 seconds in the first problem, all what we need to do is to write down what is the expression or the equation of omega as a function of time, and then evaluate it at the time t equals 2 seconds. بما انه عم نتعامل مع motion under constant acceleration, فنحن already we can immediately write down that omega as a function of t is defined by alpha t plus omega 0. But since the wheel starts at rest with omega 0 equals 0 حسب ما شفنا بالgiven, فبيبقى عنا انه هي بس equals لألفا multiplied by t. And so this can be written as we can deduce that omega at the time t equals 2 seconds هي equal للألفا اللي هي 4 multiplied by the time t اللي هو 2, and so we can write down it's equal to 8 radian per second. هيدا هو قيمة الأوميجا at the time t equals 2 seconds. So this is it for the part A. Now let's go on with the part B. And the part B can say لنا you have to find أولاً the tangential speed of the point B وبعدين the total acceleration of the point B. Okay, when they ask about the tangential speed and you are working with a rotational motion, rotating wheel, then you have to think first about the relations between the angular variables and the linear variables. So you remember we have seen a list of variables اللي هن omega and alpha and theta for the angular well for the rotational motion عموما يعني. And we have seen how to relate between the linear variable اللي هن S والV والA together with the theta, omega, and alpha. So if they're asking about the tangential speed يعني عم يسألوا عن ال V. طيب انتوا إذا بتعرفوا الأوميجا at time t equals 2 seconds, you can deduce how much is the linear speed v at the time t equals 2 seconds من خلال the relation that v is equal to r multiplied by omega, where r is the radius of the rotating wheel. يعني هي عمليا هلا هي هون احنا عم نجيب ال v للpoint p, right? ال v للpoint p هي إلها عليها is equal to r multiplied by omega, where r is the radius of the circle along which the point P is moving. بس ما انه احنا عندنا البوينت P هي موجوده على السيركمفرنس، معناتها هي موجوده على بعد radius R اللي هو الراديوس تبع الويل نفسه من الروتيشن، وبالتالي we can write down that V is equal to R multiplied by omega. So it's equal to the radius هو طلع معنا 1 meter multiplied by omega which is equal to 8. So that gives the value equal to 8 meters per second. Okay. So this is about the tangential speed. Now, what about the acceleration? We have to find the total acceleration of the point P. Okay. The total acceleration of the point P, AP, equals la how much? Be careful. Now, we don't have any relation between the total acceleration as a linear variable and the angular variables. But we know that the total acceleration, it's given by the magnitude, it's the square root of AR squared plus AT squared, where AR is the radial acceleration and AT is the tangential acceleration of the point P. وبنعرف كمان انه ال AR هي يعني نحن بنعرف انه ال AR, as we all know from the previous chapters, that it is equal to VP squared divided by the radius. هيدي نحن بنعرفها اللي هي نفسها centripetal acceleration. وبنعرف انه ال A tangential, it is related to the angular speed with the عفوا angular acceleration with the expression R times alpha. فاذا نحن بنعرف انه اي point من rigid body نقدر نجيب له tangential acceleration through this relation is equal to R times alpha, where R is the radius of the circle along which the point we are looking at is moving. ما نحن هون عن جديد عم نطلع على البوينت بي، معناتها انه الراديوس اللي عم نحكي عنه هو الراديوس للويل لانه البوينت بي مساقبه على طرفه. So let's go on and let's define how much is each component of this acceleration. طيب عندنا ال AR مثل ما حكينا هي ال VP squared divided by the radius R. So ال VP squared هي 8 فإذا squared divided by 1, and so this gives the value 64 meters per second squared. هي بالنسبة للradial acceleration. أما بالنسبة للtangential acceleration فكمان نستعمل relation between the linear tangential acceleration and the angular acceleration alpha through the angle R, through the equation R alpha. So it's 1 multiplied by alpha هي 4, 1 multiplied by 4, and so we end up with 4 meters per second squared كمان لأنه عم نحكي عن acceleration. And so from here we can deduce that AP is equal to square root of 64 squared plus 4 squared, أكيد كلها مع square root, and so we end up with the value 64.1 meter per second square. فإذا هذا هو الجواب للتوتال acceleration. بس السؤال هو هل هون بينتهي الجواب؟ يعني نحن هون طلع عنا انه ال VP is equal to 8 meters per second، هذا الجواب خالص. هون طلعت معنا انه ال AP is equal to 64 meters per second square. But is this answer enough? No, it's not enough for the simple reason. Again, تتذكروا بالchapters الماضي كنت قلت لكم انه لما يسألكم عن total acceleration يسألكم عن vector، يعني هو ما تنسوا انه الفيكتور is composed of two information، هو عباره عن magnitude وعباره عن direction. فاحنا هون جبنا الماجنتيود بس بعد عندنا ناقص هو انه نجيب الدايركشن. So this is why we need to define the angle let's call it the angle phi اللي هو بيحدد لنا الدايركشن للتانج عفوا للاكسلريشن. ونحن بنعرف انه حيلا فيكتور عموما بس بدنا نجيب له الانجل بناخذ التانجنت phi للانجل as equal to the y component divided by the x component. فبهالحاله اللي بيلعب دور الy component هي A tangential divided by A radial. So we end up with phi equals tangent minus 1 la ratio between AT and AR. So it's given by 4 divided by 64. بيطلع معنا الجواب هو عبارة عن 3.58 degree. So هيدا هو الجواب. هيدي phi equals 3.5 هي it determines the direction of the acceleration vector with respect to the radial direction. And this was the so هلا اكتمل الجواب. صار فيكم تقولوا انه صار في عندنا الجواب. It's given by 64.1 for the magnitude and 3.6 around for the direction. The last question was you have to determine as well the angular position of the point B. كمان لازم تجيبوا باخر سؤال كان الانجلر position. يعني عم نحكي عن الانجل ثيتا at the time t equals 2 seconds. How much is it? So this as well looks quite easy in this case because we know the equation theta as a function of time. بحكم انه نحن عم نشتغل ب motion under constant angular acceleration, we know that theta as a function of time is given by half alpha t squared plus omega 0 t plus theta 0, right? And we know that omega 0 is equal to 0 لأنه the wheel starts from rest. فبيبقى عندنا بس half alpha t squared plus omega 0. And so let's make the numerical application now. So we have is equal theta at the time. Oh, let's change the color. So theta at the time t equals 2 seconds. It's given by 1 over 2 times alpha اللي هي 4 radian per second squared multiplied by 2 squared اللي هو time t equals 2. omega 0 t راحت plus delta plus theta 0. هلا هون ما ننسى شغله انه theta 0 we have to write it in terms of radian لانه هون لازم يكون اليونتس للتيرمز بقلب هالايكويشن coherent مع بعضهم consistent. فبما انه عم نحكي عن الالفا هي in unit of radian per second لازم كمان الثيتا تكون in unit 1 radian. وبما انه الفاليو given هي عباره عن 57.3 ثيتا 0 ثيتا 0 equal to 1 radian هي الثيتا equals 57.3 هي 1 radian. سو بس رح نحطها بقيمتها بس بالراديان بدل ما تكون in degrees وبيطلع معنا الجواب التالي اللي هو 9 radian. So this is it. And so we can deduce again that the value of theta at the time t equals 2 seconds is equal to 9 radian. وهون we have used the fact that theta 0 which is equal to 57.3 degree هيدي الفاليو هي نفسها equal ل 1 radian. Okay. And so this is it. This is it for this problem. So let's continue with problem 31. You have to find the net torque on the wheel in this figure. You have to find the net torque about the axle through O, which is point here. If the internal radius A is given by 10 centimeter and the outer radius is given by B equals 25 centimeter. So this object, it rotates about the axis passing through O, so perpendicular to the page. So this is the figure that you see on the whiteboard. We have 3 forces, F1, F2, and F3. I call them like that just to make it easy for us to determine the torques. And so F1 is equal to 10, F2 is equal to 9, and F3 is equal to 12. This is number 1. Number 2, the radius, the inner radius who equal A equals 10 centimeter, while outer radius given by B equals 25 centimeter. Okay, now the question is how much is tau net, the net torque acting on this object? As you know, if you have an object like for example a block and you're asked about the net force acting on this object, how you would do, would say the sum of forces is equal to F1 plus F2 plus F3. And it is the same case when we deal with the rotational motion. The only difference that we're not talking about the force anymore, but we talk about the torque. And so we can write down tau net as given by, so I will just put a vector in here. So tau net is given by tau 1 plus tau 2 plus tau 3, where tau 1 is the torque of force 1 and the same for tau 2 and 3. So let's have a look at the figure, and then now we have to specify how these torque are directed. So look, what do we know about the torque? We know that the torque, let's start with tau 1, for example. So tau 1, it's given by R1 cross F1 is the vector product between R1, where R1 is the vector position of the point of application of the force F with respect to the axis rotation. فهذا هو السنتر اوف روتيشن، هو السنتر الموجود هون، والفيكتور F1 هو applied at this point. So إذا بنرسم فيكتور منطلق من الاكسس اوف روتيشن باتجاه ال F1، this is R1. بما انه ال F1 هي tangent على السيركل البراني، so عمليا ال F1 is perpendicular to R1 basically, and so that means that this is equal to ال R1 هي عبارة عن 25 centimeter, so it's 0.25 okay multiplied by the force F1 اللي هي عبارة عن 10 نيوتن. Now still we have to determine the direction of this tau 1. okay رح حطه هون، رح خليه وحطه بالاحمر. طيب have a look. لحتى نجيب الدايركشن للتاو 1 لازم نستخدم ايدنا اليمين right hand rule. so R1 على اصبعكم الكبير الاول، الاف 1 على الاصبع الثاني باتجاه اليمين، يبقى عندنا انه التاو 1 حتطلع معنا لجوا. so we have to write down then تاو 1 حسب ما طلعت معنا على الرسمه، تاو 1 هي لجوات الصفحه مش لبرات. اوكي and we are going to do exactly the same. فبقي لجوا كثير منيح. هلا خلينا نحط هلا بنرجع بعدين حنعمل البروجكشن للتاو 1 تاو 2 تاو 3. اوكي خليهم هلا بس نحط لهم دايركشن على حسب ما هن موجودين على الرسمه. let's move on with force F2. بالنسبه للفورس F2 كمان هون نفس الشيء، لازم نمد فيكتور من الاكسس اوف روتيشن للبوينت اوف ابليكيشن اوف ذا فورس F2. هيدي هي الار 2، هاي هي الثانيه. and ما انه ال F2 كمان tangent على الcircle, that means that F2 is perpendicular to R2, and we can write down therefore that tau 2 is equal to R2 vector product F2 cross. so it is كمان R2 هي 0.25 لأنه هي equal ل B في هالحالة كمان، وال F2 is equal to 9. اوكي بعد ناقص نحدد شو هي الدايركشن، رح احطها هلا هون ونشوف الدايركشن للتاو 2. so عندنا كمان بنستخدم ايدنا اليمين، بيطلع معنا R2 على اصبعنا الكبير باتجاه اليمين، ل F2 نزول على اصبعنا الثاني بيطلع معنا اصبعنا الثالث لجوا. فكمان we can deduce that tau 2 is a vector pointing inward لجوات الصفحه. بقي عندنا بس ال F3. so in the same way خلينا نرجع نرسم هون هلا ال R3 اللي هي the vector pointing to the point of application of the force F3. هيدي هي ال R3، وبما انه ال F3 كمان هي tangent على ال inner part of this wheel. so F3 and R3 they are perpendicular، وبالتالي الانجل بيناتهم يعني هو عمليا pi over 2. so الساين هي 1 and so it's R3 cross F3 it's equal to ال R3 هي 10 centimeter يعني 0.1 multiplied by the value of F3 is 12 Newton multiplied by the direction اللي هو بس اليونت فيكتور، يعني هون بدنا نحط بعد شوي بهدول البارنتيزز. بس خلينا نشوف هلا كمان بايدنا اليمين we end up with R3 على اصبعنا لفوق، ال F3 بنفس اتجاهها مثل ما هي على الرسم نزول، بيطلع معنا انه التاو 3 لبرا. so we can deduce that actually the torque of the force 3 it's pointing outward يعني لبرات الصفحه. okay now we have to take one direction to be the positive and the other to be negative. خلينا ناخذ الدايركشن لبرا هي البوزيتيف، يعني خلينا نعتبر انه هو عم يبرم حوالي الزي اكسس والزي اكسس pointing upward لبرا، فبيطلع معنا هون الدايركشن اللي لها هي عباره عن minus k للتاو 1 لانه لجوا، التاو 2 كمان لجوا بعكس البوزيتيف دايركشن فاذا minus k، اما التاو 3 هي pointing outwards يعني plus k. Okay, and so all what we have to do now is just to make the summation of all these three values. So we end up with tau net, it's equal to إذا بتيجوا بتعملوا numerical application بيطلع معكم minus 3.55 k طبعا نيوتن تايمز متر. فبالتالي بيطلع معنا انه التاو نت هي بالاتجاه النيجاتيف ساين للكي، يعني التاو نت هي اتجاهها لجوا. تاو نت points inward لجوات الصفحه. And so this is it. This is how we solve such problems. Whenever you have different forces acting on an object and produces a given rotation, tau net is the net torque acting on this object, which means the sum of the torques of all forces acting on the object that you have.